This is short problems, maybe in the multiple choice or in a short free response on the exam. You should already have these, so I'm just going to recap them. For capacitors in parallel, alright, our first rule was for the equivalent. The equivalent capacitance is C1 plus C2 plus however many capacitors. Capacitors in parallel have the same voltage. Q is equal to CV. And then we sort of had this extra rule, is that the equivalent charge is equal to Q1 plus Q2 plus however many capacitors you have. So whatever charge you have on that equivalent capacitor, each of the individual capacitors have to add up to equal that. And then for capacitors in series, the equivalent is 1 over C1. The have the same charge, capacitors in series. Q is equal to CV. And then the total voltage equals V1 plus V2 plus V3 plus however many capacitors we have. The voltage on each capacitor has to add up to equal the total voltage. Let's try doing a few questions. I think I have some that'll be relevant here. Oh shoot, what happened? Let me restart the clicker. Answer. Let's see, we've done all these. We did these, right, about capacitors?
Yeah.
Okay, actually, no, let's do combination circuits first. I'm sorry. We'll come back to this in just a bit. All right. All right, so usually when we're dealing with circuits, they'll have both series and parallel circuits combined. We call these combination circuits when you have capacitors that are in series and that are in parallel. And we apply the same rules, except we'll just sort of apply them piecemeal. That is, as we go through, we'll apply the rules to those capacitors that are in series, the series rules, and those that are in parallel, we'll apply in parallel. So first of all, let's just take this circuit. I have several parallel and series components. So for example, I have these two capacitors, which are what, in series or in parallel? These are in series. They come one after the other. And then they're in parallel with these capacitors. And then all of these capacitors are in parallel or in series with this. This is in series because it comes right after. There's no break between here and the beginning of these capacitors. Now if I want to find the equivalent capacitance, then I would first start with the smallest part that is either series or parallel. What would that be here? The smallest part of this circuit that is either only series or only parallel. Right, the two microfarad capacitors. And so I would combine those and find my equivalent capacitance. What is that going to be? A 2 and a 2 in series. That's going to be 1 over 2 plus 1 over 2, which is what? 1, right. So remember those easy numbers because it'll help you on the test. I like to give those easy numbers so that the test is a little easier. So that's a 1 microfarad capacitor. And then the next step in finding the equivalent capacitance would be to take that which is either series or only parallel. So that would be, I'm going to redraw the whole circuit here. I have a 1, a 3, and a 7, and then a 1 microfarad capacitor. What would I do next in finding the equivalent capacitance? right, I do the parallel. So I would take this part, and I would find the equivalent capacitance of this, which is going to be 7 plus 3 plus 1. And that's equal to 11 microfarads. And then I have a circuit that is just a 1 microfarad capacitor and an 11 microfarad capacitor. Right, and then I find the equivalent from that. So that's going to be 1 over 1 plus 1 over 11. Let's see, that's 11 elevenths plus 1 elevenths, 12 elevenths. That's 11 twelfths. So the equivalent capacitance of that circuit will be 11 twelfths microfarads. That's a combination circuit. Y'all have done those in lab for, or at least you will soon, for resistors, and they work similarly, but they're different. We'll see that when we get into resistors, that the rules for equivalent capacitance for resistors and capacitors are sort of flip-flopped. So be careful when you're doing these on the next test that you don't forget that those rules are different for capacitors and resistors and parallel resistors. All right. We could proceed and find the voltage or the charge on each of those capacitors. So let's say I wanted to know the potential difference across that 3 microfarad capacitor. I'm going to redraw our circuit to this point where we had our 1 microfarad capacitor here. And our 1, 3, and 7, 1, 3, and 7 microfarad capacitors. And I want to know what is the potential difference across that 3 microfarad capacitor. All right. Now, a couple of things that I know is that whatever voltage I have on the equivalent of this, remember that 11 microfarad capacitor? Whatever the voltage is on that 11 microfarad capacitor, I know that each of these has that same voltage. Because there are rules. Capacitors in parallel, they have the same what? They have the same voltage. So whatever voltage is on this capacitor is also on this capacitor, is also on this capacitor, is also on that equivalent capacitor. Right? So if I can find the voltage on that equivalent capacitor, then I can find what is the charge, or what is the voltage on this capacitor, and then finding the charge is just Q equals CV. If I know the voltage, I have the capacitance, I can find the charge. So I want to find the voltage. In order to do that, I'll need to find out what is the charge on this capacitor, and then if I find the charge on this capacitor, that will also be the same as the charge on the equivalent capacitor. Let me write that down.
Because series they have the same charge.
Because series have the same charge. So this is my 1 microfarad capacitor. This is my 11 right here. Whatever charge I have here is also the charge that I have here. Those are going to be the same. So that's also the same then. We've done a similar problem to this, to the charge that is on this equivalent capacitor, which was 11 twelfths microfarads. I have 10 volts here. All right, 11 twelfths, by the way, is 0.92 microfarads. If I can find the charge on that capacitor, right here, that's also the charge here and here. And if I get the charge on this capacitor, since then I would have the capacitance and the charge, I can find the voltage on this capacitor. Q equals CV, so V is equal to Q over C. So once I find this charge, then I can get voltage. So we're sort of stepping backwards here. All right, so here I can find the charge, Q equals CV. That's equal to 10 times 0.92, which is 9.2 microcoulombs. Then I can say, well, I have 9.2 microcoulombs here and 9.2 microcoulombs here. That's my charge in both cases. And since I have 9.2 microcoulombs, I can say V is equal to Q divided by C. That is 11 divided by 9.2. 11 microfarads, that's my, no, I'm sorry, I got that switched. 9.2 divided by 11, 9.2 microcoulombs divided by 11 microfarads. And then that gives me the voltage across this capacitor. This turns out to be 0.84 volts. Right. If I have 0.84 volts there, I have 0.84 volts here, 0.84 volts here, and 0.84 volts here. By the way, if I have 10 volts here, what is the voltage across the 1 microfarad capacitor? Not 10 volts, no. If I have 0.84 volts here, 10 volts here, what is my voltage here?
Oh, 5.2.
No, not 5.2. Right, remember, for our rule number 4, with capacitors in series, the voltages have to add up to equal the total voltage. So this voltage, 0.84, which is right here, plus this, that's equal to this, 9.16. Don't worry, we'll get the hang of this. We're going to do several examples. Alright, so then this was asking for the potential difference, so it's 0.84 volts. You could also find the charge. I would just say Q is equal to CV. 3 times 0.84 is what? 2.52 volts. 2.52 microcoulombs. It'll help you with if you keep your units throughout, because everything gets sort of jumbled up since, our Q is in units of coulombs, which carries a C, right? But our capacitors, which have a variable C, carries microfarads. So be careful with that. I try to just keep the units, capacitors being in farads, charge being in coulombs. All right? Just be aware. Just take practice to be familiar with it. All right, that's a basic combination circuit. It won't be the most difficult you have on your test, but you could have one of those. Let's try this quick test. Just what is the equivalent capacitance of this circuit? What is the equivalent capacitance of that circuit? At least I can see that circuit. In your homework, and some of the examples we'll do, you'll need to use your calculator, but on the test, likely, you'll not need to use your calculator. I try to give you nice, easy numbers so to do that. So, that should be true here, hopefully. Only about 10 more seconds. We'll stop at 135, 135. Just guess if you don't know. 5 more seconds. Okay, so we're all over the board here. Let's give this a go. First of all, what are we going to do first? We want to take the first that is either series or parallel. Which of these are just series or just parallel? 2 and 2. Right, the 2 and the 2. So my first step would be to combine the 2 and the 2. Which we already know is 1, right? And then I would combine the 1 with the 3. And then I would combine whatever that makes with the 4. So let's try that again, okay? So your first step is to combine that 2 and 2, which we know is 1, right? 1 over 2 plus 1 over a half plus a half is equal to 1 over 1, which is 1. And then I would combine that 1 with a 3 microfarad capacitor, or just add them up, the capacitors parallel. And then I would combine that capacitor with the 4 microfarad capacitor right here, and it would be in series. looking good. Just a few more, say 10 more seconds. You can ask your neighbor what they put. Almost everybody has the right answer. So ask around if you like. Ask your. All right, I'm going to stop at 1 minute. Okay, so A is the right answer. Almost everybody did have the right answer. We got led astray somewhere along the way. All right, let me show you how to do this. So A is correct. All right, guys, so I take this. As we said, this is the same as a 1 microfarad capacitor. So I have a 1, a 1, or excuse me, a 1, a 3, and this is a 4 microfarad capacitor. So these two combine to give me what? 4, right. So then I get 2 4 microfarad capacitors in series, and then I say 1 over a quarter. What's a quarter? That's 1 over a half. Let's see, a half goes into 1 how many times? Twice, right. So 2 is the right answer. A is the right answer. Oh,
is that the same thing as you put 1 over 1?
No. No, when you have capacitors in parallel, you just add them up. Yeah. Like I said, with resistors, it's different. Like when you have resistors in parallel, then you do that funky thing with the inverse bit. Alright, so be careful with that. That's where students often get confused. Because they've done a lot of resistors in lab. But when you have capacitors in parallel, you just add them up. That's on your equation sheet, if you forget, or whatever on the exam, but it's easier just to know it.
So series that 1 over the inverse thing, and it's in parallel.
Right. So 1 plus 3 is just 1 plus 3 is 4. Alright. Alright. Let's try this one. This one's a little complicated, just because it looks different from the way that we've seen it. And often if you look at circuit diagrams, they don't really look in the same way as we've been drawing them. They're more drawn out like on a grid like this. So we want to be able to just take these and rearrange the circuits so they look more like what we're accustomed to when we're dealing with these combination circuits. So that's going to be sort of the tricky part, is taking a diagram like this and then figuring out how it appears in sort of our standard way that we've been drawing, so that it looks more normal. So you can tell what's in parallel and what's in series. The way you want to do this is we generally go from the positive side of our battery, and we'll travel in this direction. And then as we go along, we'll look for breaks in the circuit, like right here. And then we'll look at points that go back to the battery. So let's just start redrawing this. I'm going to draw the battery. Then I'll draw that first capacitor. Nothing's happened there. And then up here, I get a point that breaks into 2 parts. Right. So this point right here is the same as this point. These 2 junctions are the same. I've just redrawn them a little bit differently. Okay. And then I can go and I'll draw C2 and C3. So I'll have C2, which is right here, and then C3, which is right here. Now this is where it gets a little sticky. If I have, imagine I have like an electrical current, and it wants to get back to the battery. Where's it going to go from this point? It's going to go straight back to the battery. So from this point on, it has a clean path back to the battery, just a wire. And so an electron traveling in this wire is going to bypass these capacitors completely. Whereas if I have an electron up here that's traveling, where is it going to go? It's going to break. Right, so it has 2 opportunities to go back to the battery through one of these capacitors. The point being that down here, this branch is completely separate from these 2 capacitors. So these 2 capacitors, when I draw them, are they going to be in this upper branch, or are they going to be in the lower branch? The upper branch. Right? So, so as I imagine that coming off of C2, which is right here, I come to another junction right here. So this junction here is the same as this junction. And then I have two capacitors. I have a 2 and a 2. Well, let's just write the capacitances, or the name of the capacitor for now. This will be C4, and this is C5. And then these come back together. So this junction right here is like this junction right here. It's where these two capacitors come back together. And then everything goes back to the battery from there. Right, so this circuit is the same as this circuit. These two are identical. And notice when we talked about C3, how an electron coming off of C3 will have a direct path back to the battery. We have that drawn here. It's a little circuitous because we sort of drew this little jog, but it still goes straight back to the battery. We'll do a couple examples. You have one in your homework too that are similar to this, but you'll have a question like this on the test. And we'll do a couple more examples. All right, so let's find the equivalent capacitance. Why don't you just take a few minutes? I'm going to go ahead and write in the capacitance for all of these. This is 2. This is 2. This is 4 microfarads. C3 is 1 microfarad. And C1 was 6 microfarads. You might be able to do this in your head. Yeah. Huh? Oh no, let's just wait a second, okay? Yeah, you can probably do it in your head if you remember all the distractions that we've been doing. What we got? What is it? We got tape. It is 2. Let me show you. I'll go ahead and draw it out in just a minute. So here, I have a 2 and a 2. Right? 1 over a half and a half. That's equal to 1. So this one simplifies to just a 1 microfarad capacitor. Or no, I'm sorry.
No, they add together.
Yeah, they add together. So 2 and 2 is 4.
And then you do the series.
And then we get 4 and a 4.
Which is 1 over 1/4. So we can use
1 over a half.
1 over a half of 2.
Or 2, right. I'm going to write this out in a second, okay? So yeah, so that would be 2. And then
add that to the 1, so it's 3.
I would add that to the 1. Right, so then I would have a 6.
And then it's 3.
Right.
And you get a half.
Right. Okay. Let me write all that out. All right, so just sort of quickly. 2 and 2 makes 4. A 4 and 4 in series makes 2. A 2 and a 1 in parallel makes 3. And then a 3, which is this whole thing, and a 6 makes 2. Let me write all that out. So first of all, C45, I'm going to call it, is equal to 2 plus 2, because they're in parallel. So that's equal to 4. I'm going to redraw the circuit with each step, okay? Because we're going to come back and we'll want to find the voltage and charge on each capacitor. And it's useful to have these circuits drawn out. Here I have, this is what? C2. It's 4. This is our new C45, which is also 4. And this is in parallel with C3, which is 1 microfarad. Right. And then I'll combine C2 and C45. I'm going to call that C245. The combination of capacitors 2, 4, and 5. That's going to be 1 over 4 plus 1 over 4. That's equal to 2. I'm going to redraw this. You probably don't want to redraw it every time on the test, but as you're doing it, just sort of first learning, it's probably a good idea to do that. Helps you to sort of see the circuit a little better. C1 equals 6. This is C245 equal to 2. And then this is C3 equal to 1. All Alright, and then the next step, we've done very similar to this. Here I have C1, which is equal to 6. That 2 and the 1. This is now going to be C2, 3, 4, 5. That's equal to 2 plus 1, which is equal to 3 microfarads. And then I have a 3 and a 6 in series. We've done that. That's 1 over 3 plus 1 over 6, which is 2. So my final equivalent circuit is just a 2 microfarad capacitor. That is 1 over 3 plus 1 over 6 is equal to 2 microfarad capacitors. Taking these two, which are in series, and combining them.
And that's the equivalent capacity.
That's the equivalent capacitance, right? Alright, now I have a 12-volt battery. And I could ask you, and I will ask you on the test, any one of these, the voltage or the charge. Now hopefully you can look at it and sort of think about how the charges are distributed and figure out what each of those are. And I'll do that and we'll talk about that, but we'll also work it out sort of the long way as well. But let's just think about this. If I have 12 volts on my 2 microfarad capacitor, I want to think about how these voltages are distributed across these two capacitors. Now this capacitor is twice the capacitance of this one, right? Now capacitors with a larger capacitance, do they have a bigger or smaller voltage? I'm asking capacitors with a bigger capacitance, do they have a bigger or smaller voltage? Now remember, Q is equal to CV. We talked about this before. If we hold our Q constant, if C is big, does that mean V is bigger or smaller? Smaller. So if C is big, V is small. Now that means that this one is going to have a bigger or smaller voltage. Smaller by what amount? By half, right. So this voltage is going to be half of this voltage. But I know that those two numbers have to add up to equal 12. So what two numbers, one which is twice that of the other, add up to equal 12? 8 and 4. We'll work this out the long way in just a bit, but being able to do it this way will save you a lot of time, and it comes with practice, and I think you'll do it a lot more easily. So that means that here I have what voltage? I have 4 volts here and 8 volts there. So I'm going to write that in. I have 4 volts on the big capacitor and 8 volts on the smaller capacitor. Now tracing this back, I get 4 volts here. I've already found that. What does C3 have? Remember our rules, okay? These are capacitors in parallel. Parallel capacitors have the same voltage. That's true for resistors too, by the way. But for capacitors in parallel, they have the same voltage. So whatever I have here and here. So what do I have here? I have 8 and 8 volts. So I have 8 volts here and 8 volts here. Now, almost done. I have numbers I've already found, 8 volts there and 4 volts on C1. These two capacitors are identical. They're in series. Capacitors in series have the same charge always, regardless of whether they're identical or not. But in this case, because they're identical, they're also going to have the same voltage. So the voltage across C2 will be 4 and 4 volts. They're identical capacitors, so they're going to have the same charge, and they have to add up to equal 8. All right, so I'm going to have 4 and 4 volts. I have 4 volts and 4 volts here. All right, now anytime you get two quantities for a capacitor, you can find the third quantity pretty easily, right? It's just Q equals CV. So if I fill in 2 of those variables, I can find the third. So I could also find the charge on any one of these. So for example, this one has 24 microcoulombs, 6 times 4. This one has 8, this one has 16, and this one has 16. Remember, those capacitors in series, they have the same charge. Okay, now going back, I have 4 volts, 8 volts, 4 volts. And across C45 here, I had 4 volts. Remember, that was the equivalent of 4 and 5. So what is the voltage across C4? capacitors in parallel have the same voltage. So that's going to be 4 and 4 volts. All right? Hopefully you can look at a circuit, or you'll be able to look at a circuit as we go along and be able to pick out the relationships between the voltages and how they're distributed throughout the circuit in that way. I find it's really helpful to draw out the circuit as we go along and figure out what those things are. Now, let's take this a longer way, right, and how I would go about finding the charge on these, the charge or voltage. All right, so first of all, we've done ones like this before. I would first find what is the charge on this capacitor right here. And that charge would equal to CV, which would be 24 microcoulombs. And then that would tell me that I have 24 microcoulombs here and 24 microcoulombs here. Right, because they're in series. And because they're in series, they have the same charge. And now that I know the charge and the capacitance, I can find the voltage. V is equal to Q over C. V is equal to 24 divided by 6. And similarly here. So now I find these voltages, just looking at that one in that way. And then I can do the same as what I did over here. I have 4 volts, 8 volts, and 8 volts, which I found here. Right. Now, on this top one, right here, since I know that this one has 8 volts right here, then I can say that it has 16 microcoulombs of charge. Q is equal to CV. 2 times 8 is 16. That means that I have 16 microcoulombs here and 16 microcoulombs here. It was easy for us because there was an even distribution of voltage. Either it was the same or it was nicely distributed for a nice even number. But if that's not the case, you have to find the charge on the capacitors in series and then find the voltage from that charge. All right, so now that I know the charge and the capacitance, I can find the voltage, which is Q over C. 16 over 4, 16 over 4, which is 4 volts. All right, and then that's the end. Everything else sort of carries out the rest. All right, let's do another example. I know that some of you are not quite on board with it yet, but we're going to do several more examples, and we'll have more practice. There's some in the homework as well. Let's do this one. This one's a little simpler. Consider this circuit. What is the charge on the 3 microfarad capacitor? What is the charge on the 3 microfarad capacitor? You might be able to just to look at it and figure out what the answer is, or you might have to figure out what is the equivalent capacitance, find out the charge on the equivalent capacitance, and then find out the, and then that would be your answer, actually. Doing really well so far. Those of you that have answered. Feel free to ask your neighbor what they put. Alright, y'all, let's do about 15 or 20 more seconds. And stop at 405. 405. Okay, that's really good, but need to be able to do it more quickly than that. 4 minutes is way too long to spend on that, but with practice it will come. All right, we can look at this pretty easily and say, well, these two branches are in parallel, so each of them is going to have 12 volts and 12 volts. And then you could approach it in a couple different ways. You could say, well, a 3 and a 6 microfarad capacitor, they're going to have a distribution of voltage. Yeah. No, they both have 12 volts. Yeah. Capacitors in parallel, they don't share they don't split voltage. They share the same voltage. So whatever you have on your battery is what you see on each of those capacitors in parallel. Now this 3 and the 6 microfarad, they're going to split up that 12 volts. Right? We've done this one before, right? The 3 microfarad will have the bigger or the smaller of the two voltages. They'll have the bigger one. It's a smaller capacitor with a bigger voltage. CD, that's an inverse relationship. So small c, big V. Big V, big C, small v. Right? So we also know it's going to be bigger by a factor of 2, and as that up equal to 12. So this will be what? 8 and 4 volts, right? So I could have 8 and 4 volts there. So that would tell me then that I have a charge here of 8 times 3, which is equal to C times V, or 3 times A, which is 24. Oh, and notice, by the way, that we have 24 microcoulombs here. That's good because capacitors in series, they have the same what? They always have the same charge. So I have 24 microcoulombs here and 24 microcoulombs here. All right, another way that you could do this is that you could look at it and say, well, the equivalent of these two capacitors is 2 microfarads. And I know that I have 12 volts. That gives me a Q equal to 12 times 2, or 24 microcoulombs, which is the answer, B. And whatever I have on that equivalent capacitor, the 2 microfarad capacitor, I have on each of the individual capacitors to make it up. Alright? What's my charge on this capacitor, by the way? 20, it's the same, right? Not because they're in parallel, but because they're identical. They have the same voltage, and so that means they're also going to have the same charge. So this also has 12 volts, so that's 24 microcoulombs. Alright? Want to work on speed, because you'll have a bunch of these circuit problems on the test, and you don't want to spend a whole lot of time on a simple one like this. I think I have another one. Yeah, what's the equivalent capacitance of this circuit? Find the equivalent, and then go ahead and think about what are the voltages across them. I'll give you some other questions to voltages on any one of these capacitors. So if you find the equivalent already, then go ahead and figure out what are the voltages on each of the capacitors. in just a minute, I'm going to ask you questions about the voltages across the various capacitors. So go ahead and find the equivalent first. Oh, you got it already. All right, I'm going to stop in 5 seconds at 128. I think that's everybody. 3, 6. Oh, we're missing one person, I think. 128, 130. Okay. I just don't have any jokes this morning, I'm sorry. Is that okay? All right. That's good. All right, so 2. I combine the 4 and the 4. 1 over a quarter plus a quarter is a half. That gives me 2. Then this 2 and this 2 gives me 4. And then that gives me a 4 and a 4 in series. So I'm going to draw that out. You probably don't need to, but if you want to, you can. All right, so this is my 4. This is 2. This is 2. And then that gives me a 4 and a 4 in series, which is 1 over a quarter plus a quarter, which is 2. All right. Now let me ask you some questions. What is the voltage across this capacitor? Is it 3, 4, 6, 8, or 12? The voltage across that left 4 microfarad capacitor. Well, basically, all right. We're sort of split evenly right now between 2 answers, one of which is wrong, of course. Let's go back. I have 12 here, right? So that means I have 6 and 6, right? Because they're identical. And now I want to know what these voltages are, right? These are in parallel. And then I want to know what these voltages are for the series. Think about what that means. All right, good. Starting to shift in the right direction. Just a few more seconds, okay? I'm going to stop at 1:15. Right, A is the right answer. It's 3 volts. Because I get 6 and 6 here. That means I have 6 on these. And that splits it here, 3 and 3. Let's try another one. Let's say, what is the voltage now across this capacitor? Probably have them all figured out in your mind now. So what is the voltage on that capacitor? And then in the next question, which I'll ask in just a second, I'll ask what is the voltage of this capacitor? We're going to do the red one, the 2 microfarad. What's the voltage there? We'll stop at 22. 22. Excellent. C is the right answer, isn't it? Yeah. 6 volts. Remember, we had 6 volts between these 2, 3 and 3, and this is in parallel, so I have 6 volts here. Now let's do this one right here. So what is the voltage now across this capacitor? That is the same as asking what is the voltage across this capacitor, by the way. All right, just a few more seconds. I'll stop at 30 seconds. 30. Okay, not quite as good this time, but C is the right answer. Look, I want to know the voltage across this one. If I have 12 volts here, I'm going to have 6 volts here and here because they're identical, and they split that. They split that voltage. So I have 6 volts there and there. Let's see, did we ask this one already? The 2 microfarad? Yeah, we did that one already. So this one, what was the answer to this one? Is 8. Is that right? C. 6 volts, right. All right, we're not going to do this whole problem, but I want you to think about how to draw this capacitor. This is from an old test, and I want to know how we're going to draw this capacitor. Now, we're going to have a couple different parallel and series branches. You want to first draw your battery, and then draw this first capacitor. This is obviously in series with the battery. And then up here, we're going to have a couple branches that are going to split up. And then here, we're going to have another couple branches that are going to split up. So I want you to draw that out. Don't draw it real big, because you might get it wrong, or draw it with a pencil or whatever. And then I'll help you draw it out, sort of, in our more conventional way that we've been doing things. Once you get it drawn, it's easy. Well, maybe not easy, but it's easier. The hard part is just drawing it correctly. So think about how you draw that. Start with the battery, and then sort of trace your way through the circuit, figuring out where the branches split, and then where they come back together again. Look here, folks. We come up here to our first junction, which is right here and right here. That shows our first branch. All right, and then draw what's on the top of that branch and then what's on the bottom of that branch before they come back together. Where do they come back together?
They come back together for C5 and C6.
Right, so it's at this, I think it's right here?
Yeah.
Yeah, so at this point is where they come back together. This line might be a little misleading. You can imagine this line collapses down to a point. Right, and then it goes off into this other branch right here. So go ahead and draw that first parallel branch. There are actually 2 parallel branches in this circuit. And draw the second parallel branch. I'm going to go ahead and fill these in. What's my next branch going to look like?
Same exactly.
Yeah, they look exactly the same, right? Except
6 and 7 is the
that's exactly right. So I have C6 and C7. And then on the bottom, I'll have C5. And then they'll come back to the battery from there. There are no other capacitors. Right, so this circuit looks a lot like one that we've done before. I think like once you get it drawn like this, then answering what are the voltages or the charges on all the different capacitors becomes not easy, but a lot like what we've done before. I had a question like this on every test. beginning of time. So if you want more practice, there are more things. We'll do some more in class, of course, but we'll spend a little more time on these. All right? Test is 1 week from Monday. We're going to get into chapter 3 soon, and then we might. Chapter 3 is really short. It's just on current and resistance, and then we might get a little bit into chapter 4, but we're not going to get into chapter 4 for the test. Okay. All right. I'm going to try to later next time. I'm going to try to start out with quicker questions next time. Okay, y'all can sort of drag it in a little bit. I'm not offended or anything, but I just want to let you know that we missed the question. I know it's the cold. I don't want to come on time. Have a good day, okay?